So today I am going to be explaining how to calculate the steady state model for two of the same size tank in series with each other, and we're going to use transfer functions to solve this. So let's first draw out our system. So we have our first tank, and we have two flows going in. We're going to call them U1 and U2. We know that inside of our tank we have some liquid level, so we're going to call this our height 1. We also know that our tank has some cross-sectional area that we're going to call AC. And we know that it has some cross-sectional area down at the bottom where the flow is coming out, and we're going to call that AB since it's our cross-sectional area at the bottom. So we can say that our flow out, so our Q1, is equal to our cross-sectional area at the bottom times the square root of 2GH1, since we're doing this for our first tank. And then we also know that we have a second tank of the exact same size. So we have another flow going in, which is our Q3. We have our cross-sectional area that we're going to call AC, since it's the same as our first tank. We have some liquid level height in here that we're going to call our H2. And we have some flow going out. This is going to be our Q2, which is the same formula as our Q1. We also have our cross-sectional area down at the bottom of this tank also. So we have our cross-sectional area at the bottom times the square root of 2GH2, since we are using this for our second tank. So first we are going to calculate the initial steady state heights of each of our tanks. Since we've done a problem of this type in the past, we are going to start by solving our differential equations in Colab. So first I am going to pull all of our systems that we're going to be using into our code. And next we are going to define the right-hand side of our equation. So define right-hand side. So we need to start with our independent variable, which is our time, and then we have to have a vector of our dependent variables, so one for our height and one for our flows. So now we can unpack our vectors of our height and our flows. So we're going to say that H1 and H2 are equal to H, and our U1, U2, and U3 are equal to U. So now we also know that our Q outs are equal to our cross-sectional area times the square root of 2GH, but in our problem statement we are told that our resulting flow rates from each tank are equal to 2 times H2, or the square root of H. So we're going to say that our Q1 is equal to 2 times our H1 to the power of 0.5, and our Q2 is equal to 2 times our H2 to the power of 0.5. So we can find the change in volume of each of our tanks by creating a mass balance for each tank. So we know that our volume is equal to our cross-sectional area times the change in our H1 over the change in our time for our first tank. And this will be equal to our flows in minus our flows out. So we have U1 plus U2, since those are the two flows going into our first tank. And we're going to subtract Q1, since that's the flow that's going out. And then we can do the same thing for our second tank. So we have AC, our DH2 dt, is equal to Q1 plus U3 minus Q2, since we have our Q1 coming in and our U3 coming in and our Q2 is leaving. Okay, so now we can use JAX to find the initial steady state height values from the equations that we found on the whiteboard. So we're going to return, and we're going to use JAX to create an array of our equations that we just did. So the left-hand side of our equation was the cross-sectional area times DH1 over dt. So we want the left-hand side of our equation just to be equal to dH1 over dt. So we need to divide the right-hand side of our, or the left-hand side of our equation should just be dH1 over dt. So we're going to divide the right-hand side of our equation by the cross-sectional area. So we're going to have U1 plus U2 minus our Q1 divided by our cross-sectional area, and then we're going to do the same thing for our second tank. So we're going to have Q1 plus U3 minus Q2 divided by our cross-sectional area. And our code's yelling at me a little bit because I forgot to initialize our variables. So we are going to do our cross-sectional area is equal to 2 meters squared. And we also need to initialize our U values at the beginning. So our UI is going to be equal to an array of our U1, which is equal to 2, our U2, which is 0.5, and then our U3, which is 0.4. And these are in the units of meters cubed per second. I put our U3 outside of the brackets. There we go. So now we are going to use a root solver to pull out the initial values for our steady state heights. So we're going to use root, and we're going to use lambda, and we are going to set x equal to our height. So we need to use our right hand side of our equation, and since we are looking for our initial steady state height, our time is going to be 0. We have x set to our height, and then we need to use our initial u values. And now we need to take a guess at what our initial heights are going to be. So let's just keep it simple and do an array of 1 and 1. So we're guessing that our initial heights of our tanks are 1 meter. And we can see that in our x value, our first tank is 1.56 meters, and our second tank is 2.10 meters. So now we can set this equal to our initial height values, and we are going to put dot x at the end to show our code that we are looking for the x values. Now we are going to use JAX to linearize our dynamical equations with respect to our output variables h1 and h2, and our input variables u1, u2, and u3. So to start, there are 2 parts to our state space equation. The first part is x dot of t is equal to ax of t plus bu of t. And then we also have y of t is equal to our cx of t plus our du of t. So we are going to use our y dot equation to find our matrices A and B. So to use this, we need to find h dot of t, which is equal to our Jacobian of our partial derivatives of dh1 over dt with comparison to our height 1 and height 2, and then our dh2 over dt with comparison of our h1 and our h2. So we are just going to label this as our jh, and this needs to be multiplied by our h1 minus our h1 initial, and our h2 minus our h2 initial. And then we also need to multiply this by the Jacobian of our partial derivatives for our u values. So it's respect to dh1 over dt with respect to u1, u2, and u3, and then our dh2 with respect to u1, u2, and u3. So we are going to label this as our ju, so our Jacobian of u, and then we need to multiply this by our u1 minus our u1 initial, and then our u2 minus our u2 initial, and our U3 minus our U3 initial. Okay, so now we are going to use Jacobian to evaluate the partial derivatives with respect to h1 and h2. So we're going to do Jacobian of our right-hand side with respect to our height values, so we need to type 1. So Python indexing, our t is in our 0 position, our height is in our first position, and u is in our second position. So we are going to set this equal to our jh function, and then we can evaluate this at our initial time, so 0, our initial height values, and our initial u values. So this will give us an array of 4 values. So we can see that our first value is our dh1 over dt with respect to h1, and then respect to h2, and our dh2 over dt with respect to h1 and with respect to h2. So we are going to set this equal to jh so we can pull our values easier. And then we are going to do the same thing for our u Jacobian. So we're going to have ju function is equal to our Jacobian of our right-hand side. And we are going to now pull our second values. So now we can say that ju is equal to our ju function of our initial time, our initial height values, and our initial u values. Then we can print ju. So we can see that we are given 3 values. So this is our dh1 dt with respect to u1, our dh1 over dt with respect to u2, and then we have 0 since our first dh dt does not use u3, since u3 is going into our second tank. And then we can also see with respect to dh2 over dt, our u1 and u2 values are 0, and our u3 value is good. So now we are going to use scipy.signal.statespace to find our linear time invariant representation of our system. And we're going to use this to find our C and D matrices, which will lead us to being able to isolate H2 by itself. So we are going to try to solve for our y equation that we wrote up here. So our y equation is just an algebraic expression, and when we found x dot, we used our differential equation. So finding y is somewhat easier than finding x. So we are going to have y is equal to a matrice of our h1 and our h2 values. Now, even though we are just trying to find our h2 value, we can't just ignore that we have a h1 value. So we are going to multiply this by a matrice of 0 and 1. So when you do the matrice multiplication, you will have h1 times 0 and h2 times 1. So h1 will equal 0, and it will not have a numerical value that will affect our equation. So now we need to add on our u1, u2, and u3 variables, since we cannot ignore those either, even though we don't want to have values for these. So we are going to have a matrice of our 3 u values, and we are going to multiply this by a matrice of 3 zeros, showing that we do not want a numerical value for any of these 3. So now we can create our state space model. So we're going to do sig.statespace, and we need to initialize our values for our A, B, C, and D matrices. So our A matrice is our JH, our B is our JU, and then from what we just found on the whiteboard, we need to create an array of 0 and 1 for our height values. So it only pulls our H2. And then we're also going to create an array of our u values, and all of these are going to be 0 since we are just focusing on our height 2, our h2. So now we're going to turn this into a linear time invariant representation. So we're going to name this our LTR, and then we can look at LTR, and this will give us all of our values in a state space form. Okay, so now we are going to use scipy.signal.ss to tf to turn our state space model into a transfer function. And we are going to do this in respect to our h2 and u3 variables. So we are going to use signal.ss to tf, and we are going to copy and paste our matrices into our function. And then we are going to say that our input is equal to 2, since we are doing this in respect to u3, and our u values are in our second position in our right hand side of our equation. So now we are going to set this equal to our numerator and our denominator, so we can pull these values. And then we are going to use sig.transfer function to turn this into a transfer function. So we're going to do sig.transfer function of our numerator and our denominator. So we can see that we have an array in our numerator of both of our height values, and then in our denominator we have an array of our u values. So we are going to set this equal to our h2 to u3 transfer function. So now we are going to find the step response of our linearized model, and then we are also going to find our solve IVP of our non-linearized model, and then we are going to complete the two, or compare the two. So first we need to have our h2 u3 transfer function, and then we're going to do dot step to pull out the step function. So we can see that this gives us an array of our time values, and then it also gives us an array of our h2 derivation values with respect to our h initial value. So we are going to set this equal to our time and our h2 derivation values, so we can plot this out. So I'm going to go over to my Colab plots, and I am going to grab part of this. And we are going to say that our x value is equal to our time, and our y value is equal to our h2 derivation values, but they are just in respect to our h initial, so we need to add in our h initial. And we also need to explain that we are just looking at our h2 value, so we're going to put a 1, since our h2 is in the first position of our array with respect to Python's coding. Alright, so if we look at our graph, we can see that our initial steady state is at 2.1, which is the same value that we found earlier, and it reaches another steady state of around 3.55 around 20 seconds later. So now we are going to use solve IVP to do the same problem. So we're going to use solve IVP, and we are going to use lambda, and then we're going to initialize our independent variable and our dependent variable. We're going to use our right hand side, and again we're going to say our independent variable is time, our dependent variable is h, and we have another dependent variable, our u. We have to use our u initials, but we also need to tell Python that we are looking at our u3 value, so we're going to create an array of 0, 0, and 1 to tell them that we want our u3 value, since u3 is in our third position, or our second position for Python coding, so we need to have a 1 there. And then we are going to say our time interval, which is going to be from 0 to 20. We are going to initialize our independent, or our initial h value values, and then we are going to use the method Radu. And we are also going to say that our dense output is equal to true, so we can pull these values at any time. So we can see here that we have an array of our time values and an array of our h values. So we are going to set this equal to our result. And then we are going to pull our t-plot in here. And we are going to say that we are going from 0 to 20. And we want 100 value points. And then we are going to say that our h1 and our h2 values are equal to our result dot sol. And now we can pull in our make subplots. So we are going to say, we're going to put both of our plots on the same plot to compare the two. So for our linearized model, we're going to have x is equal to 2, and then our h2 derivations plus our h initial values of our second tank. And then we are also going to copy and paste this. And we are going to say that our x values are equal to t-plot, and our y values are just equal to our h2. Oh, I put a 2 in here instead of a 1. So now we can look at our graph of the red line is our solve IVP. So this line shows higher than our step response. So we can just see that our step response is most likely going to be more accurate than solve IVP will. Thanks for watching.